Welcome to our third lesson on FRQs. Today, we're going to be talking about table problems, and what those are and what they mean. Let's do a quick overview, like we did in the last two lessons, about important concepts that you're going to see with these types of questions. So the first thing we want to know is how to approximate a derivative. Pretty common question that is asked in table problems is to approximate the derivative using the average rate of change, or the slope. All right, A-rock. Okay, that's typically one of the first questions you're going to see, and I'm going to go through two examples that show that. Another common topic you're going to see is the use of Riemann sums or rectangular approximations. You need to know left, right, and midpoint. Midpoint is a little bit trickier, I think. And then another method of approximation, actually I'll just keep this in the same bullet point, is the trapezoidal approximation. Remember, a trapezoidal approximation is when we use trapezoids, to approximate the area of the curve, and that typically will give you a better approximation than a Riemann sum. So use Riemann sums and trapezoidal approximations. To approximate a definite integral. So if you're asked to evaluate or approximate a definite integral of a table, this is what you're going to do, is you're going to use Riemann sums or a trapezoidal approximation. All right, another thing you're going to see is an average value. Average value often shows up in these. For example, if I want to find the average value of f, it's written with f and with a bar over it. This is going to be 1 over b minus a, integral from a to b of f of x dx. Okay, so if I want to find the average velocity of something, and we're given a table that represents the average velocity, you're not going to find the average rate of change of velocity. You're actually going to use this integral here. And the last thing, these are concepts from Calc 1, is the mean value theorem and the intermediate value theorem often show up as well. Okay, and I'll briefly talk about what those are in one of the questions today. All right, so that's kind of the overview. So this video is just going to go through two FRQs. And you're going to see a lot of these concepts show up in these two FRQs. So FRQ number 1. Okay, let's say we have hot water dripping through a coffee maker, filling a large cup of coffee. The amount, we'll call it C of T, of coffee in the cup, from 0 to 6 is given by some function C, and T is going to be measured in minutes. And we have this table that represents the amount of coffee in ounces as a function of minutes, time, up here at the top. So we're going to start with using this table to approximate the value of the derivative of C at 3.5. Okay, and the way we're going to do that is we're just going to look at this table here. It's pretty straightforward. And 3.5 is right in the middle of these two t values. And so for letter A, we're going to say that the value of the derivative at 3.5 is approximately equal to the slope of our function in between 3 and 4. So C of 4 minus C of 3 over 4 minus 3. Okay, all we're doing here is we're finding the slope. So y2 minus y1, that's 12.8 minus 11.2 over 1. And this is no calculator, so the math is going to get a little annoying, but 12.8 minus 11.2 is going to be 0.8 plus 0.8, or 1.6 ounces per minute. Okay, and that is the answer for the first one. All right, is there a time on the interval 2 to 4 where the value of the derivative is equal to 2? Okay. To do this one, there's a couple of keywords that they use here. C is differentiable. Okay, if the function is differentiable, that means C is continuous as well. Okay, if C is continuous, that means the mean value theorem can apply here. Okay, what the mean value theorem states is that if I take the average rate of change between 2 points on a continuous function, then the first derivative of that function has to equal the average rate of change between those 2 points at least once. Okay? And so let's calculate the average rate of change. So the average rate of change, or the slope between 4 and 2, is going to be, well, C of 4 is 12.8 minus C of 2, which is 8.8, over 2. Okay, and now we get 4 over 2, which is equal to 2. So, because the value of the average rate of change is 2, that tells us that the derivative must equal to at least once between 2 and 4 according to the mean value theorem. And so we're going to say according to the mean value theorem, it's just abbreviated MVT, there must be at least 1 point, between, I'll say 4, rather, just, so 2 is less than or equal to t, which is less than or equal to 4, where the derivative is equal to 2, because the average rate of change is 2. The average rate of change between 2 and 4. So that's the idea. Okay. Number 3, our letter C is asking us to approximate the value of this integral, 1/6 integral from 0 to 6 of C of t, and then using a midpoint sum, and then determine what this means in context with the problem. Okay, so what does it mean to use a midpoint sum here? So I'm going to go back up. So the midpoint sum, and I'll rewrite this down below, is basically saying that the value of the integral, this is for letter C, the value of the integral from 0 to 6 of C of t dt is going to be equal to the sum of 3 rectangles. Okay, the value of those rectangles, if we're going from 0 to 6, is going to be, here's one rectangle. So from 0 to 2, the base of that rectangle is 2, and then we want the C value at 1 because we're using a midpoint sum. So that's going to be these values in the middle. Okay, the second rectangle is going to be between 2 and 4. So again, the base of this rectangle is 2, and then the height is going to be the value of the function in the middle of 2 and 4, which is 3. Okay, and then the last term is going to be these values over here. Again, the base is 2, and then the height is going to be the value of the function at 5. Okay, so that's the setup. Now let's go down and let's evaluate this integral. So we want to figure out what this is. So we get 1/6 times 2, I'm just going to rewrite what we wrote before using the midpoint sum. 2 times the value of C at 1 plus 2 times the value of C at 3 plus 2 times the value of C at 5. Okay, and let's plug these y values in. I'll factor out the 2 as well. So we get 2 over 6 times the sum of these three y values. Well, we get 5.3 plus 11.2 plus 13.8. Okay, because this is AP, you can actually leave your answer just like this. So you can actually stop here, and this is no calculator, so you might want to do that. The likelihood that you make a mistake is going to be reduced if you just write your answer like that. But I'll just simplify it. So this becomes 1/3. Well, this becomes 30.3. And if we divide that by 1/3, we get 10.1 ounces. Okay, what does this mean? Well, this right here, this integral statement, is the average amount of coffee, because it's the average value function, average amount of coffee in the cup. We'll write in ounces. On the interval zero is less than or equal to t, which is less than or equal to 6. That's the average amount of coffee in the cup from 0 to 6 minutes. All right, almost done with this first FRQ. So letter D wants us to use this new function. Let's say the amount of coffee in the cup in ounces is modeled by this function here. We want to find the rate at which the amount of coffee in the cup is changing when t equals, it's at 5, okay? So I'm going to start by rewriting this function. So let's say we have a function that models the amount of coffee in the cup. Continuous function here. We want to find the rate at which this function is changing at 5. So that just means we're going to take the derivative of this and then plug in 5. So the derivative, the 16 will go away. This becomes positive 6.4 e to the negative 0.4 times t. And then the value of the derivative at this point is 6.4. E times, negative 0.4 times 5 is going to be negative 2. And so we get 6.4 over e squared. And that is the value of the derivative of this function at 5. Okay, and that's the answer for the last one. All right, let's go through one more FRQ to wrap up this video for today. And here's the mark scheme here if you want to see the answers. Okay, remember each FRQ is out of 9 points. All right, FRQ number 2. So Johanna jogs along a straight path and we're given her velocity as a function of time, and it's a differentiable function. That's kind of the setup. So up here we have time, and then the velocity as a function of time is represented in the bottom row. All right, so let's estimate the value of the derivative of v at 16. Well, similar to our last question, the derivative is going to be approximated. So the keyword here is estimate. The derivative is going to be estimated by taking the average rate of change between 12 and 20. So what that means is v prime of 16 is approximately equal to v of 20 minus v of 12 over 20 minus 12. And let's figure out what this is. So we end up with 240, that's the y value when t equals 20, and then 200 is the y value when t equals 12, over 8. We have 40 over 8, which is equal to 5 meters per minute squared. And those are the units for these ones. It's acceleration. That's letter A. Letter B wants us to determine the meaning of the value of the definite integral. The definite integral of the integral from 0 to 40 of the absolute value of v of t. Well, if we take the integral of the velocity, that gives us the displacement. But if we take the integral of the absolute value of velocity, that will give us the distance, is the distance Johanna traveled from 0 to 40 seconds. Keyword here is distance. All right, and how do we actually approximate what that value is? We're going to use a right Riemann sum now. Okay, so I'll do this kind of twice. I'll do it once up here just so it's easier to see the... Actually, I'll just do it like this so you can see the table. All right, so continuing with letter B, the value of the integral from 0 to 40 of the absolute value of v of t dt is going to be equal to the base times the right height, the right-hand side height. So the base is 12, and the height is the value of the function at 12. Next rectangle is going to be the base times the height. Well, the base is going to be 8. That's the difference between 20 and 12. So 8 times the height at 20, which is, I'll just write it as v of 20. Okay, plus the difference in the t values is 6. Oh, sorry, it's 4 times v of 24. Well, because it's asking for distance, this is negative, and so it's actually going to be v times the absolute value. 4 times the absolute value of v of 24. That's going to be the only tricky one. Plus, and then lastly, 16 times v of 40. All right, and let's figure out what this is. So this is kind of annoying to do without a calculator, but we get 12 times 200 plus 8 times 240 plus 4. So if this is asking for displacement, we would treat this as a negative number, but because it's asking for distance, we're going to treat all the y values as positive. So we're actually going to take the absolute value of 220 here. So 4 times 220 plus 16 times 150. All right, so once again, you can actually leave your answer like this, right here, this whole mess. As long as nothing is defined as a function, you can leave your answer like that, but let's just evaluate it and write units. So 240 plus 920, or 1920 plus 880 plus 2400, and that will give us 7,600 meters. And that is the total distance Johanna has traveled from 0 to 40 seconds. Let's say we have another individual, Bob, and he's riding his bike along the same path. And his Bob's velocity is modeled not by a table, but by a function. Let's find the acceleration when t equals 5. So this one's not too bad. We're just going to take Bob's velocity here, velocity function, and we're going to plug in 5 to the derivative of this. So here is Bob's velocity. And so the acceleration at t equals 5, well, the acceleration function is going to be 3t squared minus 12t. 300 will go away. Okay, and then the acceleration at t equals 5 is going to be 3 times 5 squared minus 12 times 5. Well, 3 times 25 is 75. 12 times 5 is 60. And so Bob's acceleration at t equals 5 is 15 meters per minute squared. All right, and let's wrap up this question by going through letter D. And this will wrap up the video as well. So letter D wants us to find the average velocity. Okay, so we're given the velocity, we want to find the average velocity from 0 to 10. Okay, so similar to what we talked about before, the average velocity, I'll write it as v with a bar above it, is going to be 1 over 10 minus 0 integral from 0 to 10 of t cubed minus 6t squared plus 300 dt. Okay, and we're just going to evaluate this integral. That's going to tell us what the average velocity is. So we end up with 1/10 integral. Let's actually integrate it. T to the 4th over 4 minus, this becomes 2t cubed plus 300 t from 0 to 10. Okay, the 0 terms will wipe each term out so we can ignore the 0 term. So we're just going to plug in 10 here. Okay, 10 to the 4th is 10,000 over 4 minus 2 times 1,000 plus 3 times 10, that's 3,000. Okay, so 1/10, well, this becomes 2,500. That's a fourth of 10,000 minus 2,000 plus 300. So we get 500 plus 300, 500 plus 3,000, which is 3,500. And we're going to divide this by 10. So the average velocity is 350 meters per minute for Bob. Okay, and that is our answer for letter D.